Buongiorno a tutti, benvenuti a tutti a ROMHACK. And that was all the Italian that I could pick up in the last few hours in Rome. Thank you so much. And my name is Samit. I work for Citrix in India. And my talk is about OAuth. OAuth is an open standard for token-based delegated authorization. In simple terms, it means that I, as an end user, can grant a third-party application access to the resources that I own. So my talk will cover some of the attacks that can arise when there are implementation pitfalls involved in the OAuth implementation and how we can mitigate them as well. So a little bit about myself. My full name is Samit Anwer. I work for the product security team at Citrix, web mobile app security enthusiast. And I've spoken at a bunch of conferences, including Security Fest, DEF CON China, Black Hat Asia, AppSec USA, and Code Blue in the recent past. We'll be covering why do we need OAuth, some information about access and identity tokens. So OAuth also offers various grant types, and we'll be covering a couple of them in the interest of time. Then we'll be touching upon OAuth flow for native applications. And then we'll come to some of the attacks that can happen and the mitigations, followed by a short Q&A session. A quick disclaimer, ideas presented are personal, have nothing to do with my employer. Some content has been borrowed from Brian David Campbell's slides on OAuth 2.0 and mobile devices, Auth 0, and the RFC documents. I'm a big Marvel fan, so you can expect some references to Avengers Infinity War throughout the course of the presentation. All right, coming to our first question, why do we need OAuth? Right? Let's just understand this using an example scenario. Assume you are accessing linkedin.com. You just log in, and then you see your home screen. Now, LinkedIn wants to get access to your Gmail contacts. In order to do so, it needs some form of authentication and authorization on your behalf. So let's just say that LinkedIn asks you for your Gmail contacts on LinkedIn. But this is not a good idea because LinkedIn is asking for your credentials on linkedin.com. And linkedin.com is a third-party application which is trying to access your Google resources. So you do not want to share your Google credentials with LinkedIn. That's a very bad practice. And the reasons are that the knowledge of your Gmail password allows LinkedIn to get far more access than you want to give it. It not only gets access to your contacts, but it can do anything on your behalf. It can access your drive, it can do everything pretty much. Plus, you cannot revoke access just from LinkedIn because your access sharing mechanism is based on a password, and all the third-party applications that you have shared your password with will get revoked because if you change your password, everybody gets revoked, not just one. So it's difficult to selectively revoke access from one third-party application. The third drawback is that LinkedIn would be required to store your Gmail credentials, which you do not want to do. The fourth one is that Google will be forced to support password-based authentication. So considering all these disadvantages, this is where OAuth came into being, and it's a protocol for delegating access supported by all the platforms. The scope of access granted to a third-party application can be restricted. And we can selectively revoke access from a specific third party. It avoids sharing your credentials with the third party. And the best part is that it also gives you a foundation for an authentication protocol named OpenID Connect. So before we go ahead and discuss the flow of OAuth, I want to introduce some entities that are involved in a typical OAuth flow. The first one is the resource owner. This is the end user who can grant access to the protected resources he owns. Then you have the client or the application or the relying party. This is the entity that is requesting access to the resources owned by the end user. This was LinkedIn in our case. And then we have the resource server. This is the server that hosts the resources. This was Gmail in the previous example. And then we have the auth server. This is the server that authenticates the resource owner or the end user and grants access tokens to the client or relying party. And finally, the browser of the user. So before moving ahead, there is an offline step required called client registration, wherein the client provides some information to the auth server, and that information includes a redirect URI as well. This redirect URI is used by the auth server to send back auth code and the access tokens back to the client. Once the authorization server receives this information, it generates a client ID and a client secret for the client, and then stores this mapping of client ID to the redirect URI with itself. In return, the client ID and the client secret is sent back to the client. So client secret we'll be using when we're learning about the OAuth flow. It is used for client authentication with the auth server. The client ID, as expected, can be a public information, but the client secret must be kept confidential at all times. But if an application cannot keep the client secret confidential, like a single-page application or a mobile application, then the client secret is not used at all. So this brings us to the OAuth flow at a high level. And I've listed down all the entities that are involved, starting with the end user, the client, the auth server, and the resource server. So let's say the end user is visiting this client Stack Exchange, and Stack Exchange wants to access some of the end user's information hosted on Google. So it'll show you that these are the two auth servers that the client has registered with. So it'll show you these two options. And once the user chooses Google, an authorization request is generated, and the user is redirected to Google's auth server, where he's supposed to log in. After logging in, the authorized endpoint is where the Google's auth server is going to show the authorization request to the end user. And once the user approves of this authorization request, the client will get access to the information listed on this request by getting an authorization code. So once the authorization code reaches the client can get an access token on behalf of the user. For this request, the authorization codes needs to be sent in the fourth step. And the access token can then be used by the client to access the resources. So as you can notice, there's no step wherein the end user had to exchange credentials with the client. The end user's credentials were always with the authorization server. OpenID Connect is an authentication layer on top of OAuth, and the flow pretty much remains the same, except the fact that in the last step, you get back an additional token known as identity token, which is consumed by the client application and not the resource server. The identity token is meant to authenticate the end user to the client and not for accessing the resource. So this is how an access token would look like. It is an opaque token. You cannot decode it to get some more information about the end user. And it conveys authorization, as we already know. It is consumed by the resource server. The identity tokens, on the other hand, can be decoded to fetch users' authentication contextual information. And the information could be user's name, email address, his profile information, etc. And it is consumed by the client application for populating the UI. These tokens, by the way, are called JSON Web Tokens, and This portion of the JSON Web Token is the payload portion. So this brings us to the Auth grant types. So OAuth provides various grant types based on what kind of situation there is. We'll be studying the first two because that's more or less relevant to our current discourse. So before I go ahead discussing Auth code grant, let me just create an analogy for you. And the resource server, let's say it is the Soulstone. Now Soulstone, if you remember, in Infinity War, was placed on Vormir, and Red Skull had access to that Soulstone. By the way, this is just Avengers stuff, so yeah. So Red Skull had access to the resource server right now. But Thanos wanted access to the resource server. And that's why Thanos will be our client or application or relying party. And then we have Gamora. Since she knew where the Soulstone is, she'll play as the authorization server and supervise the authorization. So here's the flow diagram for you. So Thanos goes to the resource server and tries to access it, but he gets an unauthorized message. So Thanos, the client, now redirects the request to, he redirects the resource owner to the authorization endpoint on the auth server. Now here, the end user will accept this authorization. He'll grant the authorization and get back an auth code. The auth code is sent back to the redirect URI of the client that was registered in the client registration step. Now, once the client has this auth code, it can hit the token endpoint and exchange it for an access token. And you will also notice that the client needs to authenticate using the client credentials that were given out in the client registration step. Once the client has the access token, it can hit the resource server's endpoints to access the resource. If you look at the traffic on the wire, you're hitting the authorized endpoint here of the authorization server, along with the redirect URI, which is exampleapp.com, let's say. Then you have the scope parameter, which tells the auth server that what kind of information the client wants to access. And the state parameter is used for avoiding CSRF attacks, which we'll come to when we're going through the section for the attacks. And in the response to this authorization request, an auth code is generated and sent back at the client redirect URI in the response. The token exchange request looks something like this. You'll have the auth code and the client credentials in this request, and you get back an access token as a response. Now, the advantages of using auth code grant are that it provides the ability to authenticate the client using the client secrets. And the transmission of access token is never through the browser. So your access token will not be leaked through the browser history or the referrer header at all. In comparison to auth code grant, the implicit grant is pretty much same, except for the fact that you do not have an auth code request. Instead, there's no authorization code involved. Instead, the authorized endpoint will directly give you back a token. And using that token, the client can access the resources. The traffic is very straightforward. There's just one request, and the response has the access token. But there are many disadvantages of this flow. There's no client authentication. So if your access token has chances of leaking through the browser history, and referrer header can also leak your access token. Now, we'll be considering how OAuth works on mobile clients. The gist of the flow remains same. Client initiates auth request. The end user authenticates and approves. The server returns control with the auth code. The auth code is traded for an access token, and the protected APIs are then invoked using the access token. But there are subtle differences because your native application is running on the end user's device, and there can't be a server-to-server call to fetch back the auth code or the access token. So everything travels to the end user's device. And we'll see that what are the problems related to. So here, the native application on the device is requesting the browser to hit the authorize endpoint, and the end user will see the authorization endpoint, he'll authenticate, approve this authorization request, and after the approval, the auth code is sent back to the browser, but the browser still doesn't know which app to return the auth code to. So this sort of communication requires a registration of a callback handler. And generally how apps do it is that they use something known as custom URI schemes. So here you will see that the scheme is xcommycorp.myapp. And this custom URI scheme is registered by the native application on the device. So the browser knows that if any response is coming for this URI scheme, it needs to go to this particular native application. And this is how you register custom URI schemes. They're registered in the Android manifest file, like so. So once the browser gets the auth code, it'll send back to the native application here. And the native application can then exchange it for an access token by hitting the token endpoint. Once the access token is received, the native application can directly hit the cloud APIs and get back all the resources that it wanted. So we've covered the top 4. So we've covered pretty much all the theory that we had to. And now we'll come to the attacks, and then we'll go ahead with the questions. So this attack, known as authorization code intercept attack, can happen on mobile clients, and that's why we discussed the theory behind OAuth on mobile devices. So assume this is the end user's device. You have a legitimate application, and you have the malicious application on it. And there's a browser and the auth server. So there are some preconditions for this attack that need to be true so that the attack can happen. So since it's a mobile device, we cannot have a client secret provisioned for the client, because it goes over the wire. The user can easily intercept it and figure out what the client secret is. Or the user can even reverse engineer the application to figure out the client secret. So there's no need for a client secret because it will never be secret. So the client secret is not provisioned, and the attacker manages to install the malicious application on the device, and the malicious application registers for the same custom URI scheme that is registered by the legitimate application. So you can see where this is going, right? When the authorization request is generated by the legit app, it is sent to the auth server returns the auth code, and now the browser sees that there are 2 applications that have registered for the same custom URI scheme, and it ends up giving the auth code to both of them. So the malicious application will also receive the auth code, and it can fetch the access token on behalf of the legitimate application. So in order to mitigate this sort of attack, you should avoid using custom URI scheme redirection. As we've already seen, the custom URI scheme looks something like this, where the application package name is the URI scheme. Instead, we should fall back on something known as claimed HTTPS scheme URI redirection. So here the scheme remains the same, HTTPS, followed by the FQDN of the application. The advantage of using claimed HTTPS scheme URI redirection is that the operating system provides the guarantee to the authorization server that this is the genuine application that has registered for it, because the application would have to prove that it is owning this particular FQDN. So the ownership of this FQDN needs to be proved by the application, whereas this is not so in the case of custom URI schemes. There is no naming authority at all. But if you end up using custom URI schemes, you could also use something known as proof key for code exchange, which is also known as PXE. So let's go through the flow for PXE and see how PXE can help you mitigate against the auth code intercept attack. So here, the additional step that is required is that the client generates a code verifier, which is nothing but an alphanumeric value. And this alphanumeric value, called code verifier, is hashed and sent in the authorization request. TM is the hashing method that is used, and the T code verifier is called code challenge. So the code challenge will reach the authorization endpoint, and the authorization server will store this code challenge value, which is nothing but the hashed value of code verifier. So once the authorization code is sent back, it can reach the legit app plus the malicious client. But when you're hitting the token endpoint, the auth server expects the code verifier to come in the request. And this code verifier is just known to the legitimate client and not the malicious client. So once the code verifier reaches the token endpoint, the auth server is supposed to take a hash of this code verifier value and compare it to the code challenge it saved earlier. And if both of them match, the access token is returned back. Now this prohibits the attacker, who is on the malicious client, to exchange the auth code for an access token, because he cannot know the code verifier's value. So this is a bug I found with Microsoft's implementation of Pixie. And Microsoft's identity provider, which is login.windows.net, had a faulty implementation of Pixie. So we're going to go through the demo here. So here you can see that there is a login endpoint, there is an authorized endpoint, and there's a token endpoint I'm hitting. So and they're all hosted on loginwindows.net. So in the login request, you can see that the code challenge value is present. This is, again, the hashed value of the code verifier. And then I'm redirected to the login endpoint where I'm supposed to log in. Once I log in, the auth server will return an authorization code back to me. And when I say me, it returns it to the native application. This is the auth code. And then the client can exchange this auth code for an access token at the token endpoint. But it requires the code verifier to be sent. So I've just sent the request to the repeater, and you can see that the code verifier is present and the authorization code is present. And in response, I can see the access token, identity tokens, and the refresh tokens coming back to me. The problem with Microsoft's IDP was that it wasn't validating the code verifier's value. And even if you remove this code verifier value, this request will go through successfully, and you'll still get back the tokens, like so. So very simple mistake, but worth a shot. So in case of authorization code leaks, you could misuse the authorization code to exchange for access tokens as many times as you want, because the authorization code is not one-time use here. So you get a lifelong validity of access to the resources of the end user. So if you go through the RFC of OAuth for native applications, you will see the statement that native application must implement Pixie, and the authorization servers must support Pixie for such clients. So yeah, that proves that Microsoft made a kind of a mistake. They should have probably fixed that. So this brings us to the CSRF attack. CSRF attack happens on the client's redirect URI. And in this attack, the attacker tries to inject an authorization request at the redirect URI of the client. This can cause the client to access resources under the control of the attacker. So let's see how. Let's say that there's a malicious attacker, and we have all the other entities involved. He just publishes a malicious website and lures the end user or victim into going to the malicious website. Once this happens, the malicious website generates a forged authorization response. And instead of the end user's auth code, the attacker injects his own auth code. And the client is still thinking that this is a genuine request made by the end user, and this is basically the end user's auth code. But in reality, it is the attacker's auth code. So the client tries to exchange this attacker's auth code at the token endpoint and gets back an attacker's auth access token. And when it tries to access the resources, instead of the end user's resources, the client will get access to attacker's resources. So this is sort of a login CSRF when you move it, lift and shift it to OAuth. And the client still thinks it's accessing end user resources, but in reality, it's the attacker's resource that it has fetched. So the mitigation is a very simple step, which is to add a CSRF token in the authorization request. The client needs to make this request and attach this parameter at the end. And in the response, the client expects the same value to be copied back. And if that's not true, then the authorization response is forced. If that is true, then the authorization response will go through and client can proceed with step number 4. Yeah, this is a widely known vulnerability on the client side. If the client is leaving open redirects, there are a lot of problems that can arise. So the assumptions for this attack here will be that the client is using implicit grant, although we are just using implicit grant for simplicity in explaining. It could be auth code grant flow as well. The redirect URL pattern that is registered by the client with the auth server looks something like this. So it's client sumsite.example/cb ? The star allows any number of characters to be appended to this URL. And when the auth server receives this authorization request from the client, it will match it against the pattern that is registered. So this is the pattern. And the client has exposed an open redirect on the same endpoint. So you can add a redirect to parameter and basically redirect the user who's trying to access this URL to any other website. So let's see how this happens. The attacker publishes the malicious website, which is evil.example. The victim clicks on that link, and the evil website creates an authorization request with the redirect URI as the one underlined. So if you decode this redirect URI, you'll get this. So if you remember the pattern, it is matching the pattern because there was a star at the end. So the attacker has successfully injected this redirect to, and probably misused this redirect to parameter here, to inject his client evil example website. And the pattern matches, so the auth server will approve of this and redirect the user back to the client with an access token, since this is an implicit grant. The access token is attached as a fragment and redirected to the client sumsite example. And when the request arrives at client sumsite example, the client is set up to redirect using the redirect to parameter. So it watches this particular underlined URL, which is client evil example, and redirects the end user back to the evil example website. And since the access token fragment was missing here, the browser will attach this access token to this request as well. And eventually, the attacker will get access to the access token. So client, Thanos, exposed open redirects and it has cost him everything. So please don't do that, because even if you're using auth code grant, you will end up losing your authorization code, which is, again, not so cool. So that brings us to phishing using users' trust in auth server. So let's just assume here that the attacker here has registered this redirect URI called attacker.com with the auth server. And the attacker can now create this particular forged request with the auth server's endpoint, and the redirect URI is set up to attacker.com. So when the end user sees this sort of URL, he will trust the auth server because he knows Google is a nice party, so I'm going to click on it anyway. But the redirect URI is set up to redirect to attacker.com, and the auth server has decided to trust this attacker's redirect URI. So basically, the end user ends up on this redirect URI after clicking it, and from there, the attacker can basically do a phishing attack and get whatever it can from the end user. So as a mitigation, the auth server must necessarily inform the end user that he's redirecting to another website. That's the best it can do. Yeah, this is an interesting one because this involves a particular client to be registered with multiple auth servers. So if the client has registered itself with Google and Facebook, then, and let's just assume that one of the auth server turns malicious, let's see what it can do. So the intent of the attacker or the malicious auth server here would be to trick the client to obtain the auth code or access token from a different auth server. And the only requirement here is that the client is using the same redirect URI for Google as well as Facebook or any other auth server. So again, I've listed all the entities that are involved. This is the end user, and this is LinkedIn, our client, and Google's auth server as well as Facebook's auth server. Facebook's auth server we are assuming is malicious, and then there are resources specific to both the auth servers. So the end user goes ahead and clicks on Facebook. The authorization request is generated to Facebook's auth server. And once the authorization request reaches Facebook, Facebook can redirect the end user to Google's authorization server page. And the end user ends up watching Google's authorization server page instead of Facebook's auth server page. And if this step is missed by the end user, and he doesn't notice this change and grants the access, then the authorization code will be sent back to LinkedIn, and LinkedIn will try to redeem this auth code at Facebook's endpoint. And when Facebook receives this auth code, it's going to redeem the code at Google's auth server's endpoint and get back the access token. Now the token is basically for Google's resources. So Facebook goes ahead and accesses Google's resources on behalf of the end user. So that's why it's called the mix-up attack, because we are mixing up two different auth servers and getting access to resources of different auth servers. So as a mitigation, the clients must register different redirect URIs for every auth server. So something like Google redirect URI and Facebook redirect URI would suffice. How this helps is that when the client initiates the authorization request, it knows that it is requested Facebook, but when the auth code is redirected back, it is getting redirected back to Google's redirect URI now. So there is a discrepancy here, and the client should be able to figure this out and stop the processing of next step. So in summary, we've studied that OAuth is used for delegating resource access to a third party. We also know that access tokens and identity tokens are used to prove authorization and authentication respectively. And it is recommended to use auth code grant for web applications. You need not have Pixie, but with mobile clients, you should always use Pixie. And then we covered some of the attacks. So there are a few bunch of references that are important if you want to get a head start with OAuth 2.0 and you want to go through the security considerations and best practices. Especially the RFCs are pretty informative. So I would recommend anybody who wants to go ahead with OAuth and practicing security on it to read through these references. They'll come in very handy. And Thanos has just clicked his fingers. All right. So that's some of my contact information. If you would like to get back to me, I'm available through my email address or LinkedIn. I'll be happy to take some questions. Grazie.
Okay, so we have time for a few questions. If someone wants to ask question about this interesting talk, please stand up or no question? Oh, really, guys? Okay, Smauri. Thank you, Smauri.
How often did you see problems regarding the referral leakage where the actual token is passed to the client connected to tracking systems, so for example, analytics, Google Analytics or things like that? I mean, it happens that an analytics platform is able to retrieve those tokens and use it?
That's right.
Thank you.
Hello?
Okay.
Yeah, it's quite often because I've seen it in practice myself a few times. The referral header leakage is a very common problem, and as you said, analytics is one case, but even if, let's say, that you're trying to access some resources or advertisements are shown on your website, the advertisement websites are an even major concern compared to Google, because Google you can still trust, but you can't trust advertisement agencies with your specific credentials, access tokens, and auth code. So it's a very common problem, and it's worth looking at them.
Sorry, Smauri.
Did you think just setting proper referral policy is enough to prevent all of them, all of those leakages? I mean, as a general fix without editing the client code, just setting a referral policy.
Yeah, that's one good usage, but also while doing code reviews as a pen tester, you must be aware of any other third-party integration with your client website. So any other website that is there should be, thoroughly looked through. Any referral header checks should be properly in place. So yeah, that's there.
Thank you. If you have more question, please. I cannot see. No question? Okay. Thank you, Samit, for your talk. Thank you.
Thank you.
And